Okay, folks, well, I can see we're just about to hit 1 minute after the hour, so we're going to get started. My name is Matt Thomas, and thank you for joining the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone and video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, if you're not intending to speak, please just make sure your microphone is muted and your video camera is off. Today, we're lucky enough to be joined by Ben Lashinsky. Ben's an associate professor in geotechnical engineering with joint appointments in the College of Forestry and School of Civil Construction Engineering at Oregon State University. He received his BS from the University of Delaware in 2007 and his MS and PhD from Columbia in 2008 and 2012. His research focuses on evaluating the evolution of slope instability from a variety of disturbances, as well as the design of geotechnical infrastructure under extreme conditions. And I like this note from Ben today. He says that most importantly, he has the honor of exhausting his patient family with lessons about soil mechanics and slope stability every time they build sandcastles at the beach. So with that, Ben, thank you so much for joining us today and sharing your work.
Thanks so much, Matt, and thanks everybody for having me here today. Very true about my family. I do tend to bore them at the beach, but just hearing that, I got to get out there and do some slope failures of sand. So with that said, thanks for being here. Today I'll be talking about using topographic data such as Lidar to look at landslide controls. But I'd like to start with a quick note to say that, this is the work of many people, great grad students, postdocs, collaborators, and I'm effectively just a messenger for some of the great ideas and efforts of many others, which is an honor. So with that, let's get started. I always like to start simple. So let's start with remote sensing. A lot of our topographic data is remotely sensed or done from surveying, but it depends at this point. So what is remote sensing? It's the acquisition of information about some physical subject without actually making physical contact with that subject. One type of remote sensing tool that I'm sure many of us are a big fan of at this point, it's been a godsend, is Lidar. So Lidar, if you're not sure, provides us a point cloud of points with X, Y, and Z coordinates, three-dimensional space that can be processed to infer lots of things. Biomass of trees and vegetation, bare earth, things that we might be interested in using to, say, interpret landforms. And there's a wide range of applications of this, including mapping the ocean floor in some instances or looking at biota in the ocean too. Of course, as everybody here I'm sure is aware, it is amazing for geologic mapping and landform interpretation, looking for landslides, faults, volcanoes, etc. It even guides self-driving cars. I wouldn't encourage anybody today to edit their papers the way that you see here, but any sort of self-driving car or cars that have a response to what's in front of you are actually guided by Lidar. So what is it? It's alphabet soup. Stands for light detection and ranging technology. And as I mentioned, it gives us high resolution spatial data from a laser. We have an approximation of the speed of light given the certain amount of certain conditions, and we can measure the time of flight and get all these points in space from a variety of platforms, satellite to terrestrial. And in the end, what most of us are interested in is a digital terrain model that can be processed to remove things like trees and noise. We have bare terrain. And with this, all of a sudden, what you can see is that the features of the landscape, landslides, flow areas, alluvial deposits, all this, they just pop out. And it's pretty amazing for mapping. So how can we use it to benefit our interpretation of slope stability or application of slope stability? That detailed topography can be used for stability analyses, inventorying, identifying features associated with unstable terrain, scarps, compression terraces, etc. And if you're so lucky to get a couple collections, you can look at high resolution change and start to evaluate the kinematics or the changes in a given feature. It's a spatial data set. And the nice thing about that is you can associate it with other spatial data sets of interest. Some common ones might be infrastructure. What could the impact of landslides to infrastructure be? Development, census data, risk analysis, all this, in addition to the typical derivatives you can get from topography. If you haven't had a chance, I suggest you go to Washington DNR's website. They have some beautiful art with Lidar, just showing some of these geo features, and they're magnificent. I love them. This is a great one of a fault. taken and something that you might not see so visibly from the air or even on the ground. Alluvial deposits could be prone to liquefaction. You can see Lidar really makes it pop. And of course, the reason most of us are here, deposits of past landslides. All of a sudden, the features of these slope failures, whenever they happened, are much more apparent and distinct. So why do we care? So I'll give you an example. On the left is the typical hill slope or slope failure that your slope stability instructor would draw. That knucklehead is usually me. I can already feel my students' eyes rolling when I draw these three black lines. Now, it's instructive, it's intuitive, it's the basis of a lot of our theory. But if you look on the right, reality is often quite a bit more complicated. And it's okay to have first order estimates, but sometimes you actually need some topography to isolate some of the controls on real landslide movements. So we can take this topography for stability analyses and use it for a variety of different applications, including back analyses or forensics, inversions, geomorphic relationships and scaling laws, susceptibility, just to name a few. And again, if you have several data sets, you can look at the kinematics, the patterns of movement for a given slope failure, or look at change from erosion or accretion of materials over time. So here's a brief roadmap of today's talk. I have to admit it's a bit of a hodgepodge, but I've just selected a couple topics that I think are fun to talk about, and I look forward to going through them. So first we'll go with inverse analysis of landslide inventories. So we have Lidar for a given landslide. That's very valuable in, say, mapping headscarps, cracks, zones of extension or compression, features that give us some idea of what might have happened forensically. And that's very valuable for a single active landslide. However, you can, with assumptions, of course, extrapolate some of these observations or some of these findings or a back analysis, for example, to entire landslide inventories and start to at least explore first order regional trends in the characteristics associated with those failures. So over time, we've some great students I've worked with and collaborators, we've developed some approaches to infer rupture surface geometry from topography, reconstruct pre-failure topography as an estimate, and perform 3D slope stability as a back analysis on thousands of landslides. And with all that, start to look at spatial trends relating to strength of landslides, size, and even as a proxy using strength, looking at, say, weathering in the subsurface. So how do we usually infer a rupture surface of a landslide? Well, the most classical, tried and true way is putting on a raincoat, rain pants, a good pair of boots, and walking on the landslide or walking around it. You look for certain features, a main scarp or secondary scarps, perhaps compression zones, perhaps a toe, and you map these features. And you try to interpret what they imply about how the landslide moves and where its rupture surface might be. For example, the main scarp itself is a daylighted part of the rupture surface. If you're so lucky, you might have access to a drill rig, and you can drill some borings, install inclinometers, and basically connect the dots to try and get a rupture surface. This is how it's often done for singular landslides. Of course, there's other techniques to look at, say, volumes of landslides or other things that might relate to mean thickness. There's the classical Kroon-Varnes oblate spheroid approach. You can measure some widths and lengths along the margins and depths and kind of get an idea of volume with bulking, without, etc. And then, of course, there are landslide area volume scaling laws. So there's many of these. Guzzetti and Larson really kind of investigated these quite a bit. And there's still debate about whether there are differences in these relationships for different types of parent materials and types of slides. But in general, what we observe is that area and volume tend to scale together via power law. And if you have a volume and an area, you have a mean thickness. So these approaches all have their utility. They're all valuable for certain applications in certain instances. But the challenge is that they're not easily generalizable for inverse analyses at the scales of entire inventories. So what we've done is developed some different techniques to try and kind of leverage some of the awesome elements of these approaches into something a bit more generalized in 3 dimensions. What we use is a spline, thin plate spline, where we use a set of boundary conditions. For example, the headscarp is the daylighted failure surface, as I mentioned. We can use that as a constraint, along with the margins of mapped landslides, to constrain what an approximate failure surface might be in 3 dimensions. Real landslides have complex geometry. It's not just an ellipsoid. It's not the 3 black lines I drew. It's often something complex, and splines at least allow you to capture some of that complexity and shape. Of course, there are knobs you can turn that allow you to reduce or increase the complexity, but effectively that's a calibration parameter that we've used with a series of relatively well-instrumented landslides to try and constrain what the failure surface might look like. Here's an example of 3. You can see the black dashed lines in the bottom and the red dashed lines, and 1 is the interpolation, the black one is the actual real inferred surface. So we use that to calibrate our regularization constraints and then start to apply. Now, when you have Lidar and you have a mapped landslide, you can fit a rupture surface to it, and there's definitely a variety of ways you can do it. But then another thing you can do is take a step further. You don't necessarily know when the slide happened. You don't necessarily know what it looked like prior to failure. Rarely do you have that benefit. But you can use a spline or in-painting techniques to actually just blast a hole in where your landslide is, and then reconstruct the topography. A first order, smooth estimate, sure, but put the material back in place kind of where it came from. You still have a rupture surface, you have reconstructed topography, you have existing topography, you have a couple data sets that you might start to play around with for a back analysis or an inversion. So here in Oregon, we're very fortunate. We have a great geological survey, Dogami, and they have a fantastic landslide inventory. They've really made remarkable progress ever since I started here, mapping landslides with LiDAR for that matter. And that inventory is called Slido. So we take Slido data and we reconstruct failure geometries using LiDAR from a variety of inventories, looking at trends in geology, geometry, mechanism, strength, all of this. And we tried to censor it to some level, looking at slides that kind of aren't as evacuated using some metrics like overlap, deposit, scar, etc. But it's an estimate. And in the end, we used about 7,300 landslides for our inversion. Well, we fitted these surfaces to these landslides, and we have the topography, both deposit and reconstructed, and we have a slip surface. So what we do is we look at area and volume. So as expected, both cases follow a power law, similar for area and volume, and we can see that generally the power law fit is pretty close to what's been observed in other analyses. However, we don't see as much of a trend when it comes to different parent materials. So we have this data, we see that it fits pretty well, and we notice that there's this coloring of the data. Blue means the mean surface slope is pretty gentle. Red, quite steep. And you notice that there's blue dots all throughout this analysis. Small landslides can be pretty gentle. Big landslides can be pretty gentle, but there is this little sorting of pretty steep landslides that tend to be small. So we see this kind of inverse relationship and want to investigate it a bit more. And to better explore it, what we do is we do our inversion using 3-dimensional slope stability. So I just want to give a shout out that I'm not the first one to think of this concept. There's been some awesome work using slope stability to back out strength properties to look at a variety of things, including weathering or what controls landslide size. Sean Gallen, Maureen Clark's groups have done just some cool work with this in 2D and using a variety of techniques. But what we do is just slightly different. We expand upon it a bit. We have a rupture surface, we have surface topography, landslide mass, we run our back analyses, and we use both the deposit and the source zone. For the deposit, we have this failed material. We assume the bonds of cohesion, or whatever you want to call that, are broken, and we can determine a friction angle that yields stability. We use that friction angle then and apply it to the reconstructed source zone that we estimate, and we can determine the cohesion necessary for stability. From that, we end up with 2 unique parameters for each landslide, friction angle and cohesion. And from there, we try to explore, say, relationships between thickness and strength, and maybe the implications in terms of weathering. Now, those 3 black lines, or the infinite slope drawn there, It's not for naught, right? There's still value in slope stability under idealized conditions because it provides us intuition. Some basic shear strength concepts are that coarse materials don't tend to have real, true long-term cohesion. It's mainly friction. It's disaggregated material, it's decomposed, and generally it's just a bunch of grains. Now, there are exceptions, of course, relating to vegetation, but otherwise, generally friction is keeping a lot of this material in place. Under low confining pressures, friction can be amplified. Call it dilation, or there's a variety of ways to look at it, but typically in denser materials, we see dilation that kind of amplifies friction under low normal stresses. More intact rock might have cohesion or fracture toughness, whatever you want to call it, that represents some stress-independent brittle strength. Where you have a rock fracture and it's not completely fractured, there's some bond, cemented bond, that manifests, at least overall smeared, as a cohesion. But there's friction in rock too, and it is also sensitive to confining pressures due to the asperities or the shape of those actual fractures themselves. Conventional slope stability tells us a couple things too. If I take those three black lines and I run a slope stability analysis, increasing cohesion progressively, what I see is a bigger, deeper failure surface that emerges. The more proportional cohesion, the deeper the failure surface tends to be. And that's because it needs to accommodate sufficient shear stress to overcome that cohesive strength. If I do the inverse, where it's more dominated by friction, you tend to see shallower, smaller failures dominated by slope. It approaches the slope surface. And in the case of reality, this likely means localized regions of steep terrain. Conceptually, we'd expect that weathering, when you go from the surface to fresh bedrock, would manifest as some transition in proportional cohesion, right? The further down you go, the more intact rock there is, the more that there's some bonds of cement holding that together, if you will. So what we do is we take our analysis and we plot a failure envelope for the entire Oregon Coast Range. So here's a standard set of axes you'd see for a failure envelope. There's effective stress, normal stress, and shear strength on the y-axis. And what you might note at first is that this envelope is nonlinear, both for the percentiles and the median. It's nonlinear. Typically, when we run a slope stability analysis, we're using more Coulomb failure criteria, a linear envelope, and this diverges from that. The reason is because when we look at this, say we look at strength, friction angle and cohesion, their magnitudes, effective stress, normal stress on the x-axis, which is effectively thickness to some level, we see that there is a decrease in friction angle for each of these zones, each of these percentiles, and it eventually plateaus with increasing normal stress. There's some suppression of friction. Conversely, there's a pretty linear increase in cohesion with thickness and normal stress. There's some trade-off here, which we found kind of interesting. A nonlinear failure envelope, maybe to some of you, seems completely normal and everything like that, and maybe some of you, you're not familiar with it. But they're out there. There's quite a few failure criteria that are nonlinear. The most common ones you hear about are for rock. For example, Hook-Brown or Barton criteria. And for soil, you'll also see nonlinear envelopes that basically account for dilation. If you look at the Barton criteria, and we plot our envelopes, it looks something like this. Our 90th percentile is somewhere around fractured rock, median, jointed. 10th percentile, somewhere around filled discontinuities. Discontinuities filled with gouge or minerals with very low friction angles. So we see diminished friction over magnitudes of confinement. Now, we also know that there might be a little bit of cohesion from intact rocks, certainly as you go deeper in depth. And that could also add nonlinearity that's likely merged with all the trends we observe with that nonlinear envelope. But one thing we think about is that if we look at the proportional contribution of cohesion and friction, we might be able to look at a potential proxy for weathering. So here, the x-axis is the mean landslide thickness, right? Quite a few orders of magnitude here. And you can see the distribution of landslides from our data set. We see that there is an exchange in cohesive strength, this is cohesion here in red, proportional, and frictional strength as we increase landslide thickness. And this tends to be constrained in the range where we would call it the range from regolith to saprolite and weathered bedrock up to about 10, 20 meters, right? And that happens to be where a lot of the landslides are. We see that there is some exchange of increasing proportional cohesive strength that may serve as a proxy for weathering, at least in the instance where these landslides happened. Of course, we can't discount censoring smaller landslides. This is an ongoing issue, even with high-resolution LiDAR. We can't map the smallest features always. Root cohesion or root reinforcement might also play a role, but there's a lot of uncertainty in these ranges. We break it down kind of by simple mechanism or size. For shallow landslides, the ones that are largely frictional, generally having more proportional friction, we know that weathering should be the most aggressive at the surface. It's wetting, it's drying, things are breaking down. The materials that were once rock are likely broken down into grains of all sorts of sizes and are largely frictional, of course, when not vegetated. We see that failure tends to occur in steep terrain where localized topography is the main control and it's depth limited. Rock generates soil only so fast, and soil in those steep locations only stays for so long. When you start to go deeper, well, we start to have a mix of soil, mainly frictional. We start to go into saprolite or weathered bedrock, where it's frictional, but there starts to be a couple bonded pieces of rock that might exist in that shear surface. It's partially decomposed, and you start to have more proportional cohesion. As you start to have more proportional cohesion, you need a deeper failure surface to accommodate shear stress to yield instability. These landslides are also numerous and reflect a rate of in-place weathering. And then when you go to the monsters, big bedrock landslides, they tend to encompass, so they're deep, they have large proportional cohesion, and that means we'll likely need a deeper surface or it's controlled by discontinuities. The deeper you go and the more discontinuities you have, you could possibly have suffused clay minerals that reduce friction as well, in addition to confinement. And again, you need sufficient shear stress to drive failure. These landslides are infrequent, often presumably because discontinuities and fractures and weathering is slow as you get to the depths of relevance here. Another thing to consider is that just by virtue of being large, you tend to start to encompass, either actively or passively, some gentle terrain. So you might see this relationship in being more gentle with failure. We can take these inversions and also assign them to different mechanisms. These are the mechanisms placed by Slido, and we assign friction angles, mean slopes, thicknesses, etc., to add some quantitative insight to, well, what do these mechanisms look like and what strength trends do we see? We see that translational landslides tend to have higher friction angles than their rotational landslide counterparts. Conversely, rotational landslides tend to be deeper and have more cohesion. Bedrock landslides, maybe as expected, tend to be deeper and have more cohesion than soil or debris landslides. And earth flows, for whatever it's worth, tend to have the lowest friction angles. They can happen in very gentle places where you have a lot of clay minerals and potentially very low friction angles. And this data is one thing you might use for, say, a regional scale susceptibility or hazard analysis. Which brings me to the next element that I'll go through rather quickly, mainly because Dr. Nick Matthews, this is his PhD work and his ongoing work, but I was just excited to be a part of it. So I'll share a little piece of it, and I apologize if it's a repeat, but I'm just jazzed about it. So we can take similar physics, right? Take similar physics, but instead of looking backwards into actual failures that have happened, we can start to use similar physics to look forward as a predictive tool for shallow landslide susceptibility in this case. We still use the same topographic data, LiDAR, but we can also add some other derivatives from that as well as other remotely sensed data, for example, soil moisture. And what we can do is we can develop, using the same physics, a process-based approach to look at, what would happen under a variety of disturbances. It's a model. All models are wrong, but it at least provides us intuition and insight into how strong different disturbances might be as control. So in this case, I'll quickly just focus on the role of antecedent ground moisture on earthquake timing and landsliding associated with it. So before we get into that, the basic susceptibility is considered this way. you have some cluster of cells that are unstable on their own. Naturally, since they're unstable and have insufficient shear strength to hold them in place, well, they translate force or stress downslope into metastable and stable material until equilibrium is achieved or you overcome passive resistance. So what we do is we take this unstable cluster and grow the passive zone as to yield equilibrium, aka a factor safety of 1. We have some inputs, strength distributions, for example, from the inversions I've described. Soil moisture and geotransfer functions to kind of develop some relationship between moisture and pore pressure or suction stress at depth. We try to constrain soil depth. We use Josh Roaring's great model for hill slope evolution. And what you'll see is that typically you have shallow soils at the ridgelines and deep soils in the hollows and convergent terrain. We're using Oregon Lidar Consortium Lidar for this. In this case, our study site's about almost 1,100 square kilometers. If we wanted to look at rainfall, and I won't focus on that today, you can use any sort of IDF input. And in this case, I just want to focus on earthquakes just a tiny bit. In this case, we run a pseudostatic analysis where PGA is our main input, right? And we use it for scenario-based events for a possible Cascadia subduction zone rupture event. So for a given set of conditions and one strength property, you end up with something like this. You have some boundary conditions on ridges and channels, but what you'll see is that you start to get discrete shapes. It's not just a slope map anymore. And that's great and all, but it doesn't reflect the uncertainty associated with material properties. So what we do to at least start to probe that likelihood is we run our analysis for the whole histogram of strength values associated from our inversion. For low strengths, everything wants to fail. As you go to higher strengths, less wants to fail. And each one of those strength values has a probability. When you combine it and the probabilities associated with it, you'll see that some zones have high susceptibility and some low. So one of the driving questions that Nick and I chatted a whole bunch about, and Nick really kind of brought this home, was, you ever wonder what happened if the big one happened in the wet winter months versus the dry months? And there's been observations about this in the San Francisco Bay Area, in Hokkaido, et cetera, basically asking, if it's pretty wet out, will we have a lot more landslides? So these questions revolve around antecedent moisture as a control on landsliding. So for a given site, we can get a time series of SMAP data, that's soil moisture active passive from NASA, to get surface moisture and its uncertainty, so standard deviations over time. And as expected, there's a clear seasonality that you see here, where in the winter months here in Oregon, it's pretty wet. And I can confirm it's pretty wet here. And then in the summer months, it's pretty dry. So we use this as an input to start to evaluate, well, what about the big one happening in August versus February? So what you have here on the x-axis is the water year. On the y-axis is basically failed area or landslide density, however you want to look at it. You'll notice that just generally, there's a trend that follows that seasonal moisture naturally. It's a changing input. And you can see that if you have an earthquake, say a 9.0, you can see that you might see 2, even 3 orders of magnitude more failed area if it's very, very wet. Now, there's a lot of things we can't incorporate here, but at least as a first order estimate, we can see that there does seem to be a strong control here. So seasonality seems to be very strong. But even for a given wintertime month, say February, we still see differences between a relatively dry winter and a wet winter. And that might be in the order of double to 1 order of magnitude different landsliding. And of course, the bigger the earthquake, well, the stronger the shaking and the more landsliding we have, at least for these simplified conditions. We can look at the distribution in landsliding as well. It's a spatial analysis. If we go with a magnitude 9 earthquake, we see that landslide density is concentrated in the west for dry, mean, wet conditions. And you can see that there's a slight increase in density when you go from dry to wet. You can see that over here too. There's a variety of reasons for this, most of which are intuitive. It's steeper, it's wetter, and you're closer to the fault rupture, so shaking is stronger. So we see that from our analysis. We can also back out relevant data that might help with kind of just generalizing what causes failure in a landscape. In this case, a yield acceleration. We can run this analysis for fixed intervals of PGA and see what causes failure at each PGA. And when we understand what causes failure at each peak ground acceleration, well, we can start to generate maps of yield acceleration, the acceleration in which slope failure occurs. If we go from dry to wet conditions, we see that yield acceleration in many locations starts to drop. It takes less shaking to cause failure, and that areas that were once not really susceptible to failure are now susceptible. We can look at this from a variety of susceptibility thresholds and see that for a given susceptibility threshold, what proportion of the landscape has a greater yield acceleration than some threshold of interest. So another way of basically looking backwards to generate susceptibility or hazard maps. This project initially pretty much focused on evaluating impact of earthquakes, particularly for lifelines in the state of Oregon. So the Oregon Coast Range is beautiful. If you've ever driven through it, it's an amazing place. It's full of landslides. And we only have so many highways connecting the populated Willamette Valley with the Oregon coast. So these are important places for recovery, important thoroughfares for recovery after the Cascadia subduction zone event. So we performed some assessments on at least several lifelines. I'll show one here in the Coast Range, looking in February for a February event. Let's take a magnitude 8.7 earthquake, February antecedent conditions, and we can look at susceptibility here. You can see the highway coming through here. This is Oregon 6, and we see higher susceptibility in the west as stated before. We can also apply buffers to these slope failures, or even use very simplified runout analyses, Heim's law, et cetera, to kind of just say, all right, where does this volume go as a first order estimate? And how does it spatially overlap with right-of-way, with infrastructure? We can use something like the PRISM method to estimate the overlaying volume of the road or the loss of PRISM, and we can get an idea of cumulative volume along this entire roadway. If we assume a rate of excavation or emplacement of fill, well, we can start to estimate closure time from this alone. And in this case, for 1,000 cubic yards per day, we're looking at 94 days of closure time. So that high resolution topography allows us to look at first order characterization of lots of things: magnitudes, morphology, strength, weathering, susceptibility, and even planning level evaluation of impact. And that's been facilitated by some of these recent advances in the availability of these data sets, as well as physics or process-based models, which are timeless. One thing that I'll basically end in this third part of this presentation is looking at change with Lidar. I think my favorite thing about this type of tool is when you get several data sets and you can start to actually quantify how things change that we in a way that we can perceive but not rarely quantify on our own. So there's no better place to look at change than the Oregon coast. So the Oregon coast, it's always sunny there. It never rains. It's a very calm environment, which is absolutely not true actually, but we have lots of erosion there. If you've ever driven 101, and I encourage you to, it's beautiful, you might enjoy sweeping views of the ocean. And the reason for that is you're on a headland or on sea cliffs, and you might have to slow down every once in a while for an uneven grade. Well, you've just driven over a slump or an active coastal landslide. And erosion is one large element of forcing a lot of these failures. So we're in a project, we're on our 6th year, looking at monitoring several coastal landslides, as well as 7 kilometers of sea cliffs, using a variety of things, including terrestrial LiDAR taken twice a year, some in situ instrumentation, some of which has long passed away, UAS LiDAR ad hoc, as well as other surveying techniques and GPS monitoring, et cetera. And the idea for this is starting to develop techniques to evaluate sea cliff failure or impacts of coastal landslides stemming from this erosion that we're seeing and is likely to worsen with sea level rise. Here is a typical low tide day in February. This is not even very stormy. You might notice there's no volume to this, and pardon the quality, but I've turned off the volume because there's some salty language. And the reason for the salty language is because indeed that is an 80-foot piece of driftwood being hurled like nothing up onto these boulders here. You would usually hear the rattling of boulders as well being hurled with these waves. And you can imagine that when it's high tide or there's a bigger storm surge, all of these projectiles are hitting the base of the bluff underneath this video. And that is a pretty abrasive force. So we can see significant retreat in a lot of these locations. Here's an example of retreat we've observed over 3 years at one of our sites, Beverly Beach, a lovely place with a great campground, by the way. What you see is that red, dark red represents 2 meters of retreat, while blue represents 1 meter of accretion or buildup of material. And what we see here are generally that there are these long pockets of red along the toe. Those are zones where water is making contact, waves are making contact with the Seacliff, projectiles swept up with the water or eroding the Seacliff, and you have just constant retreat in the wintertime. You'll also notice zones above it where there's still quite a bit of retreat. You'll see a notch forming in many of those locations and eventual overhang failures of the rock above it. This is very soft sandstone. And you'll also notice that there's subaerial weathering in some of these zones, slumps, etc., and a bit of accretion. But you can see that in some of these locations, we're seeing over 3 years, 1.5, 2 meters of retreat at the toe. And that eventually translates up the Seacliff. So we see a variety of mechanisms, slumps, overhang failures, toe retreat, all this stuff. And it serves as a basis, as an input for a prediction or a model to look at the process of retreat over longer time scales. We can take the bare earth Lidar and create a series of cross sections for our analysis. We can take these cross sections and evaluate stability. We can do back analyses to get strength of actual slumps, and we can assign strengths to all of the cross sections and begin our retreat analysis. For this analysis, we assume 3 different mechanisms. Scour, that's all based on hindcasted and observed total water levels, and we can consider sea level rise as an input here going forward. Overhang failures manifest from overcoming the tensile strength of rock. Once a notch is formed, we can evaluate that as the geometry evolves. And eventually, when oversteepened, you'll have full cliff collapse. A slump will happen, right? It's just too steep. What we do is we integrate all this into a model that looks at this progression or this evolution over time. Scour is applied, overhangs can happen, cliff collapse can happen. And we can consider other things like armor or groundwater, etc. So here's an idealized, not real version of a Seacliff. You can see a notch forming, overhang failures happening, and eventually what you'll see is that you'll have a full cliff collapse. Now, I should have labeled this better, but the green line here is basically the armor deposited from that failure. Usually that armor disappears much faster than this analysis, but we can incorporate for the delay or the feedbacks between that. Once the armor disappears, well, the process starts again. There's your notch, your overhang failures, and eventually another collapse. We can apply this to all the transects that we get from this topographic data. And I'll play this a few times, but you might notice some notches forming and some overhang failures. On some of these ends, you can see some slumps have occurred over time. And this is for an 80-year projection at one of our sites. So I'll let it play one more time. There's some failures that are quick, some that take a while. And again, you can see the oversteepening of some of these sea cliffs along this site. And we can apply these models to get an idea of how long will it take for this erosion to manifest in loss of right-of-way, loss of highway. So we can take the outputs and interpret change, lateral retreat at any arbitrary elevation. For example, the toe or the crest. Just as a guide, we have retreat on the x-axis and the y-axis is just where it is in space. And red represents today, pretty much. Blue represents 2100. And we can see at the toe of the sea cliffs, generally, changes are gradual. It's slow. It tends to follow the retreat rates we observe based on current projections. But you will see some white gaps in here, meaning that at one of these times, there is a sudden movement or a sudden retreat that exceeds what you would expect from just that constant scour. In some of these areas, it's quite large. These little white gaps effectively represent overhang failures. The larger white gaps represent full cliff collapse. And when we look at the crest of the Seacliff, which is away from where the wave scour is happening, or from where all the action is, we can see that when we actually manifest in some retreat that might take out a shoulder or part of a lane, well, it's intermittent in time, it's sporadic. And we can see that indeed, some of them happen late in the analysis, some early, but we can at least start to overlay this, and this is ongoing work, we can overlay this with impact to highway. So these analyses provide an estimate of predicted retreat, looking at sea level rise, estimated total water levels, and the evolution of geometry of sea cliffs. So they're using just some of the simple lateral erosion processes. We can also use this as an input, both the observed erosion rates from change analysis, as well as long-term erosion. We can use that to kind of apply it to larger coastal landslides, not just slumps, but look at the debuttressing effects that we see from erosion and collapse of these sea cliffs. Because you might often drive on 101 across a landslide that's pretty far from the ocean, but that debuttressing still might manifest in that landslide marching the highway towards the ocean. So we investigate that too. We have this data, which serves as an input. What we do is we take a series of landslides. We use our same rupture surface analysis, and we can characterize transient slope stability as the geometry evolves for these coastal landslides. In the case of instability, it'll move. It'll move until it's stable again. And we evaluate movement using finite difference solver for the conservation of mass. And we can incorporate those erosion rates we see, the retreat at the base of a lot of these landslides as a time-dependent function. So what we can see from this is really isolation of the effect of erosion on landslide advance. We know many of these landslides are driven by groundwater. We know that many of them are also driven by erosion, but this allows us to look at just the effect of erosion, or at least estimate to what strength is that a control. For movement, we use the conservation of mass approach. It's very simple and certainly an estimate. We're not considering much bulking, etc., but we can at least model downslope movement. And as a landslide moves downslope, it finds itself in a more stable condition, of course, until material is eroded away. We use masks to basically look at where we expect erosion to occur based on total water levels, and we remove material via retreat rate in those areas where it's applied. And we have this erosion zone that we can see that eventually controls the advance of these landslides. And it looks something like this. Now, this is super aggressive erosion with like time scales of maybe like 500 to 1,000 years. So bear with me though, it's meant for illustration. But you can see retreat occurring at the toe. Here's the highway. You can see it marching towards the ocean. It's being dislocated with this erosion. You can see a headscarp forming and the body of the slide moving forward. We can use these approaches to basically evaluate, well, what's the relationship between retreat and advance? So it's a busy slide, so bear with me. But intuitively, the more erosion you have, the more advance you have. If you look at the axis of this plot, this is your initial landslide volume for very idealized geometries in 3D. Here's the advance in meters. And when we go from blue to red, blue is little erosion, red is a lot of erosion, right? We see that smaller landslides, if we go this way, tend to see more advance for the same amount of erosion. We're removing more buttressing material proportionally. Another thing that is a second order control on advance is the aspect ratio of the landslide. So for example, if you have kind of this squatty, kind of wide, but not very long landslide, an aspect ratio of 0.5, let's say, versus a narrow, long landslide, same volume, you'll see that this aspect ratio of 0.5 is more sensitive to erosion because you're removing more proportional material. So this is one thing we observe from here. The debuttressing is amplified, at least as a second order control from aspect ratio. You'll also notice that some of these lines end. Eventually, if you erode away enough material, the landslide goes dormant or is completely eaten away by the ocean. So smaller landslides tend to hit dormancy or disappear more quickly, but eventually that landslide moves enough to be laid in a flat position and just be eroded away. We can extrapolate this to kind of isolate to what level erosion is control on landslide advance. We see steeper landslides tend to advance a little faster, and we can actually look at real retreat rates. So we look at 3 landslides and some that were available in the literature that have time history, some of which were done by observed by some USGS folks and Dogami folks, like Carmel Knoll and Johnson Creek. And we can compare this plot, which is purely advance from erosion, from lateral retreat, to the actual movement. So for Johnson Creek and Carmel Knoll, we see that the erosion-driven advance is much smaller than the actual advance observed. This suggests hydrologic controls, hydrologic forcing, is much more important for the advance of these landslides, at least in the term of observation. For Arizona In, which is a big deep-seated landslide that actually had a series of horizontal drains placed to maintain groundwater, we can see that the erosion rate, the theoretical advance from erosion, is just about the same as that from the other condition here. So it's not being driven by groundwater, but purely by erosion. And we're starting to see, indeed, there's a series of failures occurring at the bluff at Arizona In. Now, with all this said, not all coastal landslides are really driven by erosion. Some are just too big. And I'll pick my favorite example. I think it's the favorite example of a few people in this Zoom room. And I've seen some good presentations here actually on Huskaneden. But if you haven't been to the south coast of Oregon, Huskaneden certainly deserves a stop. The Huskaneden landslide is about 20 million cubic meters. It moves anywhere, depending where you are, from 2 to 4, even 5 meters a year. And an interesting thing about it is that it has surge events, like a lot of earth flows, that are periodic. So in 2019, for example, it decided to move up to 40 meters, even more, after a pretty big rainstorm. The interesting thing about this, and Adam Booth's group's done some cool work with this, is that, well, the advance or those surge events don't necessarily correspond to very wet years. There's no clear discernible trend there. It just kind of follows this periodic behavior and of course is driven by water, but not purely so. So in this case of the surge event, it closed Highway 101 for 2 weeks. Here's a drone image of it. You can see seeps coming out of the ground here. It's quite an observation. There's an excavator for scale, my favorite thing for scale here. And you can see that there's this active zone of extension. You can see significant dislocation on the southern end of the margins. And there's actually a zone of compression down below. And there's little failures that are extensional all the way up through the mass. Here's another image. You can see some of the seeps just kind of building a channel through here. This excavator was actually operating to try and get the road open while it was still moving in the order of centimeters an hour. So we collected some UAS LiDAR and compared it to some of our previous terrestrial LiDAR collections to evaluate change via some manual feature tracking. And we wanted to look at kinematics. When we plot it all up, we see that the displacements, this is lateral displacement, are largely focused on this steep area where the surge occurred. And it's in the order of up to 40 meters. Ironically, this is where the highway and many previous iterations of the highway, by the way, are built. There was also movement downslope. You can see extension here and then compression down here, all the way down to the Seacliff. There was some movement near the beach with some uplift noted, likely driven by the compression of this surge event localized in this zone. And the erosion here is in the order of 30 to 50 centimeters a year, but the movements clearly are much larger. Here's a point cloud visualization of that uplift at the toe. Here's the old Seacliff. Here's the new one. One geologist told me that the toe of this earth flow existed somewhere in the water. And I didn't believe her originally. I'm like, that's just too crazy. That's crazy. Well, I owe her lunch. She was right. You can see here the new Seacliff that is formed purely from heave, from the compression of this relatively flat terrace of landslide deposits at the base of this earth flow from this surge event. So this is all preliminary and hand waving, but we're continuing to work on what controls these surge events. What controls the periodicity of them in time? If it's not just some big rainstorm, well, then what is it? And one thing we've been looking at doing is doing some numerical modeling, treating it as a continuum and evaluating, say, the kinematics, extension and compression, how it evolves, as well as looking at, whether there's some yield in compression that eventually results in a surge event. Do we reach some limit for a surge that's driven somewhat by water, but largely by time? So this is something that we've been playing around with, and there's just some little kitschy animations showing kind of what we're looking at. We see that there's some compression. There's a compression zone down here, an extensional zone, similar to what was observed in the surge event in 2019. So with that said, I've talked for a while. Better consideration of topographic data or using this amazing data sets are now starting to be more and more available. We have some of the physics that we know well, or the ideas that you all have, can enable some unique insight into landslide processes or what controls landsliding. Lidar is a tool. A lot of things we use are tools, but it does help us interpret kinematics, processes, and extend these concepts to hazard and risk. My favorite element of it, and I'm glad I know people who are experts on this, are change analysis. It gives us a quantitative way, gives us a way of putting a number on what we actually see and understanding how important it is, particularly as it relates to the magnitudes or mechanisms of destabilization. Some of the regional scale analyses I've shown you require coarse assumptions, but still give you a first order set of valuable information towards planning, or at least better understanding Earth surface processes. And this is a biased one, but I always believe there's promise injecting elements of slope stability towards various scales, local scale to regional scales, both as inversion and prediction techniques. So with that said, I just want to acknowledge a whole bunch of people who've been involved in this work in a variety of ways, including students, postdocs, some of which are at the USGS, some of our friends at Dogami, and of course, some of our sponsors. But this is the work of a whole bunch of people, and I'm just lucky to be the mouthpiece. So with that said, I'm happy to take any questions or feedback or whatever you have. Thanks for having me.